Cool. All right. Welcome, everybody. Sorry for the late notice on the remote class. Car troubles. I needed a car. So today we're talking about trigonometric substitution. It's one of my favorite ways to integrate functions, specifically functions that have something that look like the square root of 1 minus x squared. So as you're aware, we've integrated this from -1 to 1 about a million times. And that gives you an answer of pi over 2, right? It's half of the area of a full circle of radius 1. Today, we're going to learn how to just find the indefinite integral of this function. And so we can find other areas underneath the half circle, okay? So a few announcements. There's going to be a quiz after class today over what we cover today. Make sure to get that done before midnight. And don't forget about exam corrections. Try to get those to me by Friday at the latest, so I can go through and make sure that you did everything correctly. And if you have any questions about the exam, you can always come ask me about anything that you missed, and I can help you out with corrections. You don't have to do those all on your own. Okay, so any questions about these two announcements? Also, don't forget about homework. Homework's important. All right, so trigonometric substitution. Today's the day. Today, we finally learn how to integrate this thing. Okay, how to find an antiderivative of the function, the square root of 1 minus x squared, and also a ton of other functions that we couldn't integrate before. We're going to learn how to integrate them today. Okay, so integrating functions that look like the square root of a squared minus x squared, those previously were impossible for us to do. Today, trigonometric substitution allows us to do those. Okay, that's the main motivation for learning about trig substitution. It's also going to let us evaluate integrals that involve functions of square root of x squared minus a squared. That's not very surprising. If it can integrate this, it should be able to integrate this. And then also we're going to learn how to integrate stuff that looks like the square root of a squared plus x squared. And not only things that look like this, but also powers of this. Okay, so I mean, if I square that, we already know how to integrate this. But if I take this to the -2, then we're also going to be able, using trig substitution, we'll also be able to integrate something that looks like this. Now, I will say trig substitution isn't the best way to integrate something that looks like that. We're going to learn maybe tomorrow, but definitely next week, how to tackle something that looks like this using another method. Okay, but trig substitution would work if you tried it on this. Okay, so that's the main motivation. We want to integrate functions that look like this, this, and this, and powers of those things. Okay, so anytime one of those things show up in an integral, it's safe to bet that you're going to be using trig substitution. Okay. So before we do trig substitution, let's remind ourselves of a few things that are going to be very important. First of all, SOHCAHTOA. SOHCAHTOA. If I have a right triangle, then I can scream SOHCAHTOA to know that sine of an angle theta is the opposite side over the hypotenuse, the length of the opposite. So here's the opposite, here's the hypotenuse. So SOH. So cosine of theta is adjacent over hypotenuse. Adjacent over hypotenuse. SOHCAHTOA. Tangent of theta is, well, O over A, opposite over adjacent. Okay, so those are going to be some very useful things to know. So in particular, we're going to be making a lot of substitutions that look like, instead of saying like u is equal to x squared, we're actually going to be plugging in for x. We're going to make a substitution that looks like x equals sine of theta. We're going to be seeing this a lot today. So on this triangle, if sine of theta, x is equal to sine of theta, is x, well, that's the same thing as x over 1. So something we're going to be doing a lot is we're going to make substitutions that look like this, and then we're going to be setting up a triangle that looks like, well, here's theta, so that means the opposite over the hypotenuse is x over 1. So this is a triangle that corresponds to this substitution. Okay, and if that's the case, then what is the adjacent side? What's the length of the adjacent side? Or how could I find it? This is a right triangle, so someone's name should be popping into your head.
Pythagorean theorem.
Yeah, Pythagorean theorem. So using the Pythagorean theorem, this last side is 1 squared if you want. So 1 squared minus x squared. Okay, so didn't even need to play hangman there. SOHCAHTOA. A few other things that are going to be very, very useful are our Pythagorean identities. So sine squared x plus cosine squared x is equal to 1. And then you can divide this through by cosine squared x to get our other Pythagorean identity. So sine squared over cosine squared is tangent squared x plus cosine squared x divided by cosine squared x is 1 equals 1 over cosine squared x. Well, that's going to give me secant squared x. Okay. These are going to, really, these are kind of the basis for trig substitutions. So, and why are they the basis for trig substitutions? Well, if I have an integral that looks like this, and I make the substitution x is equal to the sine of theta, then that's going to mean that dx is cosine theta d theta, and I can use this triangle to simplify the integral into a trig integral that's going to have sines and cosines and powers of those. And we know how to handle those now. Okay. So that's the main idea behind trig substitution. So let's look at this specific example to see what's going on. I'm going to walk you through this example so we can see what's happening. So anytime I have the square root of 1 minus x squared, remember, I mean, this isn't from -1 to 1 like it was before when we've done this. But remember, this curve is still a circle, right? It's the upper half of the unit circle. And this was that's sort of the motivation for this substitution. People looked at that and said, there's a circle happening, so probably sines and cosines I should use somehow. Okay, so coming back here, I'm going to make the substitution x is sine of theta. Okay, x is equal to sine of theta. And here's why. When I find dx, because I need to substitute for x, and I also need to substitute for dx. Well, dx is cosine of theta d theta, right? So when I plug this in to this integral, I get the integral of the square root of 1 minus sine squared theta, and then dx is cosine theta d theta. Okay. And you might look at that and you might say, why did we do this? This is even more complicated. Now I have a 1 minus something squared, and now there's a cosine outside, right? But the reason we did this is because of these identities, right? These are the real workhorse of trig substitutions. So if sine squared x plus cosine squared x is equal to 1, then that means 1 minus sine squared x is cosine squared x, right? So this is equal to the square root of cosine squared x, or sorry, theta. We're using thetas here. Cosine squared theta times cosine theta d theta. But then the square root of cosine squared, well, that's just cosine. So I get the integral of cosine theta times cosine theta, which is the integral of cosine squared theta d theta. Okay. Questions so far?
Wait, what just kind of happened right there? I was writing
So
something down.
no, you're fine. The square root of cosine squared, that turns into cosine. So really this this right here, this just simplifies to cosine theta, and then we have times the cosine theta. And so that all simplifies to cosine squared theta. April, you have a question?
Yeah, sorry. Why couldn't we have chosen like cosine for substituting for x? Why did we choose?
Wonderful question. I'm so glad you asked that. We could have. We absolutely could have chosen cosine. And then the only difference would have been cosine of theta here. And when we take dx, we would have gotten minus sine theta. But that's the only difference. Everything else would work exactly the same. And in the end, we would end up with minus the integral of sine squared theta.
Okay.
But everything else works exactly the same. And if you prefer to make, with integrals like this, if you prefer to use x equals cosine theta, go for it.
Okay.
Yeah. Any other questions? All right, so this integral is one of the annoying cases, right? This is when we talked about yesterday integrating trig functions. This was the annoying case where we have to use the fact that cosine of 2 theta is 2 times the cosine squared theta minus 1. So rearranging this for cosine squared theta, sorry, I should have had a theta up here, cosine 2 theta. So rearranging for cosine squared theta, this is 1 plus cosine 2 theta divided by 2. I'm going to write a 1/2 out in front like that. Okay. So our integral then, we're looking at the integral of cosine squared theta, d theta. This is 1/2 times the integral of 1 plus cosine of 2 theta, right? So this is 1/2 times, well, I can integrate this piece by piece, right? So what's the integral of 1 with respect to theta?
Theta.
Theta, perfect. Theta plus the integral of cosine of 2 theta. Well, if you don't see it right away, you could use a u substitution, right? You could do u is 2 theta, then du is 2 d theta, or 1/2 du is d theta. You can make that substitution, and when you do that, you'll find that this integral is 1/2 times the sine of 2 theta, and then plus some constant. Okay. So we're almost done. This last part, I think, is not the trickiest, but I think students forget how this last part goes. So let's look at this. I was asked an integral in terms of x, right? I have an answer. We're done integrating. I have an answer, but it's in terms of theta. So I need to convert back into x, right? So let me erase this. So we have, this is 1/2 times. Well, remember, x is the sine of theta. So what is theta? If x is sine of theta, then theta is what? X is sine theta. I need to solve for theta. So I take the inverse function of sine, right? And we don't deal with that a whole lot, or we haven't until now. But the inverse function of sine, you just write sine inverse, or if you want, you could write arc sine. But either way, if x is sine theta, then theta is the inverse sine or the arc sine of x. Okay, this is why that integral was so hard to do and why I just ignored it until now. Now we have the tools to do it. Okay, plus 1/2 sine of 2 theta. Now, here and always, you're going to need to use a trig identity that I will give you. This isn't a class about memorizing a ton of trig identities. The only trig identities that I want you to memorize are the Pythagorean identities and this one. Okay, every other trig identity I will give you. So we need to know that sine of 2 theta is 2 times the sine of theta times the cosine of theta. That's one of the keys to doing this problem here. Okay. So let's draw that triangle that we had before so we can see what's happening. Here's theta. X, remember, x is the sine of theta. So that means sine of theta is opposite this side over the hypotenuse, this side. So x is x over 1. So we have x 1. Now, could you have done like 2x and 2? As long as this side divided by the hypotenuse is x, whatever you choose is fine. But the easiest choice here would be opposite side has a length of x, hypotenuse has a length of 1. Okay. And then that makes the adjacent side the square root of 1 minus x squared. So we have to substitute for sine of 2 theta, which is 2 times sine theta cosine theta. So there's the 2. What is sine of theta looking at this triangle?
X.
Yeah, just x. It's x over 1. Also, I mean, that's just the substitution I made, right? X is the sine of theta. And then what is the cosine of theta looking at this triangle? Well, remember, so, ka, toa. So cosine is adjacent over hypotenuse. So what is the adjacent side?
Square root of 1 minus x squared.
Square root of 1 minus x squared, perfect. Divided by hypotenuse, that's 1. So we're done once I add a c. And so simplifying a little bit, this is 1/2 times the arc sine of x plus 1/2 times, because this 1/2 will cancel with that too. I'll be left with 1/2. X times the square root of 1 minus x squared plus some constant. And you can see now why, again, why we weren't able to integrate this before. But now that we have some more sophisticated tools under our belts, we can integrate on to find the area underneath the circle now between any two x values, not just plus and minus 1. Okay, and that's the general strategy of trig substitution. Everything we did here is, there's going to be very little change going forward. You'll make slightly different trigonometric substitutions depending on what the integrand looks like, but that process of you make the trig substitution, x is equal to some trig function, you simplify, and then hopefully you can then do the integral, and then you use this triangle to plug back in for theta. That's in general how these problems all go. So in general, if you're looking at integrating a function that involves the square root of a squared, so in particular, this has to be a positive number, right? A squared is positive. Okay, so if I'm looking at integrating the square root of a squared minus x squared, then we do the following. Step one, make sure it's not a function that you can integrate without trig substitution. Because in this integral, this integral here, we know how to do. That's the arc sine of x over a. This is one that you divide everything by a squared in the bottom, right? And then you're supposed to recognize it as the arc sine. Okay. How would you do this integral here?
U substitution.
Exactly. That's a U substitution problem. And this one is also a U substitution problem. So you want to make sure U substitution is definitely easier than this. I think it's, I'm not going to pretend that it's not. U substitution is definitely, if you can do a U substitution, you should do a U substitution. Okay. But if you can't, then the key step in integrating a function that has the square root of a squared minus x squared is you let x be a times the sine of theta, or if you prefer, a times the cosine of theta. Okay, that is the key step. Then you do exactly what we did. You simplify, integrate, and then plug back in for theta. Okay. Questions on that?
Actually, I do. Do you mind if we kind of like, can you go over like step by step just through the problem again? Because I kind of got lost like halfway through it.
Yeah, absolutely. I can actually, let's look at this integral here. Or would you rather, let's look at this integral. So we're looking at a new one where you have to do a slightly different substitution, but it's the same process. Okay, so with this integral, I can't do a U sub. I can't, this isn't just the arc sine. This is an integral that we have to use trigonometric substitution. Okay, so this is of the form the integral of x squared over the square root of, you always want to write it as something squared, that 4 is 2 squared minus x squared. Okay. So I have to make a U substitution. X is going to be what? It's not just sine of theta this time. This time it's actually going to be 2 times the sine of theta. Okay. Does everyone see why? We have a squared here. Back here, we want to make the substitution x equals a sine of theta. Now, if you prefer to only deal with ones, you could do the same thing that we did when we were looking at the integral that gave us the arc sine. You could just divide top and bottom here by 4 and then make a U substitution. But this is sort of a shortcut, so you don't have to do that every time. Okay, or I guess divide top and bottom by 2, really. So dx, if x is 2 times the sine of theta, then what is dx?
2 cosine theta d theta.
2 cosine theta d theta. Perfect. All right, so we have then this integral is equal to, now we just plug in everything we have, and really this is slightly easier than u substitution in that you don't have to do any solving down here. We're letting x be something, so we can just plug straight in whatever we get here. We just plug that in for dx. We don't have to do any weird solving for that substitution. Okay, so x is 2 sine theta. So x squared in the top, we have 4 sine squared theta for that x squared up top, divided by the square root of, well, 2 squared minus 2 cosine, or sorry, 2 sine, 2 sine theta squared. And then dx is 2, which I'm going to write out here, 2 times cosine theta d theta. Okay, so this is equal to, this is 2 times the integral of, we still have 4 sine squared theta. I'll write the cosine theta up here as well, divided by, the bottom becomes, and this is again the key, the simplifying under the square root is always kind of the key step after you make that substitution. So the square root of, both of these are going to have a 2 squared. So I'm going to factor those out. 2 squared is 4. And when I do, I'm left with, well, when I factor the 2 squared out from there, I'm left with 1. When I factor the 2 squared out from here, I'm left with minus sine squared theta. That's d theta. But what is 1 minus sine squared theta?
Cosine squared.
Cosine squared, exactly right. So this becomes, I did not give myself any room. This becomes 2 times the integral of 4 sine squared theta cosine theta over the square root of 4 cosine squared theta. Again, because sine squared theta plus cosine squared theta equals 1. So 1 minus sine squared theta is cosine squared theta. Okay. But then that just becomes 4 sine squared theta cosine theta over the square root of 4 cosine squared theta is just 2 cosine theta. Okay. Questions on that so far?
Yeah, I have a question.
Yeah.
If you chose to, like, could you just get rid of the squared in the bottom of the square root, like before you factor or without factoring, and would you have gotten the same thing or something?
When you took, so which step right here?
Yeah, like if you just, because there's a square root and then there's a squared on each thing, could you just like cancel those out?
Careful. I see what you're saying. No, because the a squared minus b squared, that's not a perfect square. That you could write that as a plus b times a minus b, but that doesn't just when you take the square root of that, that doesn't work as nice as we want it to, sadly. But you do have to make the trig sub use the trig identity to write that just as cosine squared.
Okay.
Any other questions? All right, so who can see what we do next?
You can
Okay,
take one
so-
of the cosines.
Exactly. Cancel those cosines. And I got a 2 there, a 2 there. I'm going to cancel. And so this becomes 4 times the integral of sine squared theta d theta. Okay. And this is, again, we need to use the fact that cosine of 2 theta is, now I'm going to use 1 minus 2 sine squared theta. Right? Or that gives me sine squared theta is equal to 1 minus cosine 2 theta. I'll write 1/2 out in front of that. So this becomes 4 times 1/2 is going to give me, well, I'll write it out. 4 times sine squared theta is 1/2 times 1 minus cosine 2 theta d theta. So 1/2 will cancel with 4 to give me 2. So this is 2 times the integral of 1 minus cosine of 2 theta d theta, which is 2 times. All right, what's the integral of 1 with respect to theta? Well, that's just going to be theta minus, again, you could do a u substitution, but we just did this, we just did the integral of cosine of 2 theta in the previous example and found that that was 1/2 times the sine of 2 theta plus c. And so this looks almost identical to what we got before, but slightly different. So let's draw out, come on, let's draw out the triangle that we get from this. Theta. Remember that the original substitution we made was x is equal to 2 sine of theta. So that tells me that sine of theta is equal to x over 2, right? So in this triangle that we're setting up to help us plug back in for theta, what should my sides be labeled? What should the opposite side to theta be labeled?
2.
Oh, careful. The 2 is going to actually be here. I'm glad that you saw the 2 though, instead of just the 1. The opposite side though is going to be x. And then opposite over hypotenuse gives me x over 2. Yeah. And then that means the adjacent side, using the Pythagorean theorem, is 4 minus x squared. That's the right triangle. All right, and then the only other thing that we need to do is write this as theta minus 1/2 times, remember sine of 2 theta, and I will always give this to you. Sine of 2 theta is 2 times the sine of theta times the cosine of theta plus some constant. All right, so let's plug back in. Theta, well, sine of theta is x over 2, so that means theta is, well, take the arc sine of both sides. So theta is the arc sine of x over 2. Cancel these. Minus sine of theta. Well, sine of theta is x over 2. And what is cosine of theta?
The square root of 4 minus x squared over 2.
Perfect. Exactly right. Square root of 4 minus x squared adjacent over hypotenuse. Wonderful. Plus some constant. And you can simplify that further if you want, but this is your answer. Okay. So, I mean, that's kind of the hardest these integrals with square root of a squared minus x squared get. You can move that square root of a squared minus x squared around to be in the top or in the bottom and have other x's going on, but you're always going to do the same process. X is equal to a sine theta, make your substitution, do the resulting trig integral that we now know how to do, and then plug back in for theta. Okay. So the process, once you learn it, never changes. Okay. So do we have any questions about this? If we do, that's fine. I understand this is a departure from some of the stuff we've done before. Okay. So let's look at this integral, the integral from 0 to 1/2 of 1 over 1 minus x squared dx. Okay. So first of all, is this just an integral that you can do? There we go. That you can do using u substitution or anything? Or is it an integral that you know off the top of your head? The answer, what? Sorry, what?
I was gonna say, isn't that arctangent?
Yeah, careful. If this was plus, then you'd be exactly right. But the minus actually screws everything up. But yeah, I'm glad that you recognize with the plus it's arctangent. But here we're going to get something completely different. So here we do need to do another trig substitution. Okay, so you guys, everyone take a few minutes to try to come up with the trig substitution. I'm going to pause my share. Can you see those writing? Good. All right. I'm going to pause my share. I'm going to write down what I think the trig sub is. You guys do the same. All right. What do we think the trig sub is? What did we make x?
Sine of theta.
Yes, exactly right. X is the sine of theta. And that makes dx cosine theta d theta. Now, if you want, you can change the bounds the way we do with u substitution. If I were you, I would not. I feel like it gets very messy. So I would first just find the integral or the indefinite integral of 1 over 1 minus x squared and then plug in my bounds in terms of x. So let's do a trig sub to find the indefinite integral, and then we'll plug our bounds into that. So I plug in x is sine of theta. Well, that means I'm plugging in 1 over 1 minus sine squared theta, and dx is cosine of theta d theta. Okay. Equals. All right. You guys simplify that for a second. I'll simplify as well, and we'll see if we get the same answer. Okay. So what did we do next?
I multiplied the cosine of theta in the fraction we had.
Yeah. So yeah, you can make the cosine theta go up into the numerator. And then what did you do about the denominator?
Doesn't 1 minus sine squared theta equal cosine squared theta?
Perfect. Exactly right. So combining those two things, the cosine in theta and the cosine squared theta in the bottom, the cosine theta in the top and the cosine squared theta in the bottom, you can cancel one of those out from each, and then you end up with the integral of 1 over cosine theta. But that 1 over cosine theta is secant theta. So we're looking at the integral of secant of theta with respect to theta, right? This is one of those integrals that you just have to know, okay? Does anyone remember it? If not, that is fine. Eventually, you'll need to know this, but this is the natural log of the secant of theta plus the tangent of theta plus some constant. We're going to do a definite integral, so the constant doesn't matter a whole lot here. But that is what we get here. So I have an answer. It's in terms of theta. I need to turn it into an answer in terms of x. So let's draw out our triangle. Here's theta. We said x was sine of theta. So what side of this triangle should be labeled with an x? Or how would you, let's just say, how would you guys label the sides of this triangle? I'll label mine.
I did the opposite as x. The hypotenuse is 1, and then the adjacent is the square root of 1 over x squared.
Perfect. Exactly right. That's exactly what I got. Now, if we had made a different substitution, if this had been like a 4, then we would have said x is 2 sine theta, and then the hypotenuse would have been a 2. But that's not what we have here. So, I mean, we have to work with what we have. All right, so if this is the triangle we're working with, and it is, then what is the secant of theta? Or in other words, what's 1 over cosine theta? Well, first just say, what is cosine theta?
Adjacent over hypotenuse.
Exactly. So cosine of theta would be square root of 1 minus x squared, right? So then secant of theta is 1 over that. So we're going to get natural log of secant of theta. Secant of theta is 1 over square root of 1 minus x squared. Okay. And then what is tangent of theta?
X over the square root of 1 minus x squared.
Perfect. Exactly right. Plus some constant. Okay. All right. So we have this antiderivative in terms of x. So that means the integral from 0 to 1/2 of 1 over 1 minus x squared dx. Was that what it was? Yes. Well, that's going to be equal to, I just plugged in, I can write this as 1 plus x over the square root of 1 minus x squared, right? I'm going to evaluate this at x equals 1/2 and x equals 0. Okay. So this is then equal to, well, I'm going to get the natural log of, well, 1 plus 1/2 is 3/2. divided by the square root of 1 minus 1/2 squared. So 1 minus 1/4, that's 3/4. So there's when I plug in x equals 1/2. And then what do I get when I plug in x equals 0? Well, I'll get the natural log of 1 over 1. What's the natural log of 1?
0.
0. Exactly right. So this is the natural log. Everything in here is positive, so I can drop the absolute value signs. This is natural log of 3/2 divided by, this is really the square root of 3. I can do the square root of the 3 over square root of 3 over square root of 4. So square root of 3 over 2, like that, which is natural log. By the way, if you had written this as an answer on an exam, that's great. You would get full points. The rest of this is just simplifying with arithmetic. So this is the natural log of 3 over the square root of 3. Okay. Questions on that? If you type that into a calculator, natural log of 3 over square root of 3, do you do it? Yeah, that's about 0.55. 0.5. All right, so was every step of this clear? So again, the key steps, really, recognizing that you need to make that substitution and then simplifying that using the Pythagorean identity. Okay, and then the rest is integrating stuff that we've integrated before and then plugging back in for theta, sine theta, cosine theta, secant theta, all that jazz. Okay. All right, so I'm going to mention how we do integrals with square root of a squared plus x squared. We're not going to get to do an example. We'll pick up with examples tomorrow of stuff that looks like this. But the idea is almost exactly the same. The only difference is when I have the square root of a squared minus x squared, well, I let x be a sine of theta, because then when I do that, I'm going to get a squared minus a squared sine squared theta. Why did I do that? Which is the square root of a squared times 1 minus sine squared theta. And then I can use the Pythagorean identity to simplify that. When I have a squared, the square root of a squared plus x squared, well, then I'm going to use the substitution x is equal to a times the tangent of theta, because I'm using the other Pythagorean identity. 1 plus tangent squared is equal to secant squared. Okay. When I do that, I get a squared plus a squared tangent squared theta, which is the square root of a squared times 1 plus tangent squared theta, which is 1 plus tangent squared theta. Again, that is secant squared theta. People, the mathematicians who went before us, went through a bunch of trial and error and found that this is the correct substitution to make, because you end up with the square root of a squared secant squared theta, which is just a times the secant of theta. So when you have integrals with square root of a squared plus x squared, you're going to make the substitution x is a tangent of theta, and you're going to get a bunch of things with tangents and secants, which is why we talked about that yesterday. So notice when x is a tangent of theta, then dx is a secant squared theta in theta. But the process is, other than a different substitution, once you make the substitution, the process is exactly the same as when we made the substitution. X is a sine theta. You plug in, simplify, do the integral, solve for theta using a reference triangle. So tomorrow we're going to pick up here and evaluate this integral. And this means that the quiz is going to be due tomorrow now. So quiz is pushed back to tomorrow. Quiz pushed to tomorrow. Okay. So practice. If you have any questions, come to my office hours. I'll work with you through a ton of examples until you feel comfortable with trig substitutions. Okay, so thank you all for being here. I will see everybody tomorrow. I will be in person tomorrow, and we'll do more trig substitutions. So have a great day, everybody. Stick around if you have any questions.
Thank you.